show you an algorithm running, which is very simple. Yeah, it's already converged basically. What you see here, this is the iterations of the algorithm. Okay, so it's doing like 20 iterations, and this is what it started with. And then I run the algorithm. This is what I end up with. So it's quite good in that case. Of course, you know, there's no reason that this should look exactly like that. You know, you're only using the fact here essentially that there are kinds of isolated clusters, or not clusters, but the isolated pixels, which are likely therefore to be noise essentially. Maybe we're looking at another example. Sorry, it's converged vector again, but you know, it's kind of, it's not bad, right? It's doing okay. And remember, this algorithm knows nothing really about ones or digits. The only thing it's assuming is that there's some level of smoothness. Clean is smooth. Smoothness is next to plainness. Now the question is, so you know, how do you do this? Well, one way to do it, very very simply, is to say, well, look, what I want to do is I want to find essentially that x which maximizes the algorithm. But let's just do maximum over x over this vector of some function of x. In this particular case, this function of x has the following form: f of x. I'm just going to say this x is a vector now. I'm going to sort of put all these pixels into a long vector. Okay. This vector, this function, is of the form something like the product over the size of this pixel of some function phi of xi and yi, the ith element of the pixel, times by some other function over neighbors on the graph. So I've got one factor per neighbor on this grid, which is some psi of xi and xj. And these are all specified functions. This is actually of the form I e to the, I don't know what I called now, gamma xi yi, I think I called it. And this was the product over neighbors of e to the beta, I think we called it xi xj. And any constants of proportionality which make this distribution normalized don't matter for this maximum likely, this map state. We don't care about that here. Okay. So that's it. You've got a known function. In fact, you could even take the logarithm. That doesn't make any change, right? The most likely state of the logarithm is also the most likely state of the function, because the logarithm is a monotonic function. So this means that in general, that state, the state which maximizes f of x is equivalent always to the state which maximizes the log of f of x. Obviously, assuming that f is defined for this sort of positive. This is generally true. So if you wanted, you know, numerically, you could say, well, this is causing me a headache. I've got a million pixels here. Taking the product of these million quantities is I'm running out of precision to operate on my computer with that. So you say, well, okay, maybe I'll take the log. So I'll do sum over I. And the log of this is just gamma xi yi plus sum over non-neighbors of beta xi j. That makes your computational life easier, your numerical life easier. You still have to find that function x, this binary variable x, which maximizes this function. Okay. So you can say, well, you know, this looks really easy somehow, because if this were just continuous variables, this is just a quadratic form, and if we do this with matrix algebra, it's really easy. It's just some simple matrix inversion problem. But remember, these are binary, +1, -1 variables. These y's are specified. These are our known corrupted pixel states. So we have to find that state now which maximizes this function. So to take it from me, there's a half problem in general. There does exist a polynomial algorithm for this particular problem, but a generic simple thing you can do when you're desperate is to say, well, I could start out with some guess of the solution, right? Say maybe I could say x is equal to y. In other words, I start out, for example, with the corrupted version as my initial guess for the solution. And I just want to maybe improve locally the solution. So I could say, let's look at a particular pixel. Let's call it, say, xi. And I could just change xi from its current state to the opposite state. I could flip it around. And I could just see whether or not that increases this function value f. If it increases it, I could say, well, that seems to be a good thing to do. That's an improved solution. So I'll like that. I'll stick with that new x. And then I'll choose another pixel and I'll flip that state. And I'll see again whether or not that improves or not the function value. And I'll just keep doing that, iteratively selecting states or variables to flip the state. You see what I mean? So it's a bit hard to, it's easier to say it than to write it down as an algorithm. But this is a very, they've got very many different names. You could call it the world's dumbest optimization algorithm. That would be one reasonable name. It's called, the statisticians call it iterative conditional modes. Such a grand title for such a simple idea. It's called, in optimization, you would call it something like coordinate-wise optimization. But you just, each of these is a coordinate. Xi is a single coordinate. You're just conditioning on it. You're just doing coordinate-wise optimization. The one way to think about it is that this is a little bit tricky to do, but if these were continuous variables, they're not in this case, but you could write down, x1 and x2, and you've got some kind of function. And you're trying to find this optimum point here of this function. That's what you'd like to find, the x1 setting and the x2 setting, which maximizes this function. And one thing you could do is you could say, well, I could start with some guess. This is my say my x1, x2 guess. So let's say x2 initially. So this is your x1, x2 guess at round 1. And then you can say, well, actually, let's fix x2 and let's maximize with respect to x1. Right? So you could say, well, let's fix x2. Let's maximize with respect to x1. So in other words, I look now at the slice of this function, and I find that state along this function which maximizes that element. Maybe it's here, something like that. Okay. And you do the similar thing. Now you switch. Say, well, actually, I'll fix x2, and I'll find x1, which maximizes. So maybe it's now it's here or something like that. And you fix that one, and you maximize here, etc. And you start to zero in on this optimum. So this is a coordinate-wise thing. And of course, you could do more complicated things. Where you could say, well, I could say, condition upon a subset and maximize over a small. I could say, if I had 3 variables, I could say condition upon 1 and optimize over 2. I don't have to just optimize over 1. So that'll be a generalization of this. So you would get, in principle, better solutions that way. And this procedure may work. It's obviously not obvious, but it may be. It's pretty obvious. It's going to converge to a local optimum of this function. Okay? It may not necessarily converge to the global optimum, because you could have, a simple example where you have a function here, which is called, say, 2 isolated hills, And this one is actually got a value, plus 100. It's got a value, say, plus 10. And if you start here as your initial guess, your x1, x2 is here, you might do something like this. You start there, and you might start to zoom in with this optimum. But if you started over here, these are your original x, then maybe you go to this one. That's a better solution, right? So the solution for this, if you've got a function certainly which is, not got a single optimum, it's multimodal, then there's no guarantee that this coordinate-wise iterative conditional modes procedure will find you the best solution. And this is true. The same thing is true for the discrete case. When these variables are discrete, it's hard to draw that situation. Tricky, but it's the same conceptual idea. And there are even pathological cases in a case where there's unimodal for which this iterative procedure doesn't work either. You can get trapped in kind of, cyclical behavior. You never actually converge. That's also possible, but it's rare. So, and it's clearly true that well, it's maybe not obvious, but it's the case that in this image situation, you have local optima. You have many, many local optima, exponentially many local optima. So we know the simple iteration scheme is not guaranteed to find the best global solution. It doesn't. It can get trapped. But it's pretty rare, I think, in this case to see a situation which is, gives a really terrible solution. Well, this is pretty terrible, actually. Is it? Well, it's kind of hard to say. So this one here, this is maybe a little bit unfortunate. You may be, but bear in mind this guy doesn't know anything about ones. He's not saying, there's no prior that says you must only have a single connected blob. And if you look at the original data, I don't know, might be something going on down here. I don't know, it might not. It may be just trapped in a local optimum. It's hard to say. I mean, what I could do, I could try to run the exact algorithm, which is some complicated thing, which you will learn more about if you do the vision lecture, or if you want to read the last chapter of my book. Yeah.
But you actually give it quite substantial information by limiting the number of neighbors and the second product. Because you limit it to 4 neighbors, and so the smoothing region.
Yeah, but remember this is it's a kind of collective phenomenon. So it's not the algorithm is not say that you look at a pixel here and you look at its 4 neighbors and then you decide. The decision is not only a function of its 4 neighbors. It's not, you see what I mean? It's not like, because it's hard to say, if you were doing that, right? You said this guy here, for example. Another example. Maybe this one here. Right. So maybe it's got 1, 2, 3. It seems to have quite a lot of neighbors which are, which are white. But actually, in the end, he turns out to be black. So even though there could exist pixels for which, in the original corrupt image, there are more neighbors which are white. But actually, in the end, the optimum says that that pixel should be black. That could happen because there's a collective thing. Because overall, it might be that, well, actually, this guy's white, but look, he's surrounded by mainly black pixels. So in fact, he should really be black, which would mean that that guy should be perfectly black. He doesn't have that many white neighbors anymore. You see what I mean? So it's a kind of collective phenomenon, in some sense, which is what makes it a fascinating problem in some ways. Okay. So that's a a very simple optimization procedure that you can apply generally, not just in this scenario. Okay, so the other thing I should say is that going back to here, so somebody pointed out that so this normalization constant here, of course we could absorb this, by the way, into any of these factors that we want. That's also doable. But usually it's more convenient to define these factors separately to start with, and then say, well, there exists an additional overall normalization constant. And this constant may not necessarily be easy to compute. It could be very, very hard to evaluate this. So in a sense here, in this particular problem, I just wrote down these things. It's very easy to specify these local potentials. But it doesn't necessarily mean that I don't know what this normalization constant is here. For this particular map problem, I didn't need to know it. But if, for example, if somebody said, well, what is it? Do you know what it is? Which you may need for some other problem. That's a real headache to figure out, because I'd have to sum over all of the exponential number of configurations of this graph. Right? There are 2 to the power d configuration states of this distribution. So it's impossible to do it naively. There does exist, I believe, for this particular special case, some remarkable algorithm which may get somebody, a big prize in mathematics, which works. But it's not at all true. So it's lifetimes of mathematicians' work to figure these kinds of things out. The math case is a bit easier. That's been known for quite some time. But this figuring out Z for this problem is really a big challenge. Okay, so this is all, by the way, kind of just motivation. So I want you to sort of get some idea that this graphical model stuff is not just a theoretical thing. People really do use them a lot, but we'll concentrate a little bit more on the theory aspects in this course. Because now we know what a Markov network is. So we'll ask the same questions before. What does it mean in terms of independence, dependency statements, and what is the kind of graphical picture going on there? So here's a question. For this particular Markov network, are B and C independent given A and D? So, well, we just have to figure it out. So what is, for example, what is B? Is it independent of C given A and D? Well, we can figure out what is, if this is true, if B given A, D, and C actually is just bad, then clearly it's B is independent of C given A. This is what the statement means in principle. So let's figure out what is P of B given A, D, and C. We plug in Bayes' rule. This is the joint divided by the thing on the right. And then we plug in the fact that this joint distribution actually is, well, we can use the fact that the normalization, the margin here is just the margin of the joint. And then we plug in the fact that we have this particular Markov structure. So here I'm just absorbing, actually, by the way, if there is a normalization term, I'm just going to absorb into one of the potentials, because it's irrelevant for this particular situation. So I've got this product terms here. So I've got, these are the cliques. AB is a clique, AC is a clique, CD and BD is a clique. And I've got the denominator got the same thing. Now we notice that some things are going to cancel here. So this one cancels with that. Why is that? Because we're summing over B here. So this term here is not a function of B. So we could, in principle, we could pull that out as a prefactor and then it would just cancel. The same holds for this term here. So when we've done that, this term here, there's no C dependency left in this expression. So whatever that is, it cannot be dependent on C, so it's some function only on A and D. So therefore it's true. So it's independent of this expression does not depend on C. It's independent of C. So they are conditionally independent. Okay. So that's interesting. So what are the general kinds of ideas here? So here's a graph, it goes an undirected graph now. So A, C, and B, C, or maybe some Z if you want to write that down. If we sum over C, what happens? Well, we get a sum of products here, which doesn't necessarily factorize into a function of A times by a function of B. So what that means is that there's no reason to assume that the marginal is going to be independent. So just kind of effectively sort of summing over C kind of causes, if you like, dependence between A and B. But similarly, if you condition upon C is some fixed state, then clearly this is a function of A times by a function of B. So conditioning upon C in this case does give independence. This is actually the opposite of what we had before. So before, with the belief network, we had that marginalizing over C, if C were a collider at least, would have given rise to independence. And conditioning upon C, if C is a collider, would have given rise to dependence. It's the opposite situation here. So these graphs are completely different in terms of the language or the semantics of the language. Okay. So this plays a similar kind of game to what we did before in terms of these connection graph style ideas. So the basic idea is that so conditioning is going to cut the path, but marginalizing is going to connect variables in the path. So it's the opposite of the belief network situation, right? So here is our B and C conditionally independent given A and D. Well, condition upon A, so that path BAC gets blocked, it just becomes a factorized term. And similarly, BDC path also gets blocked, which gets a factor. So that's in the new graph, basically we just get this kind of thing. There's no path which is connecting B and C anymore. Similarly, you could say, is B and C independent given A? So we have to marginalize now over D. Well, the top path is actually going to give rise to factorization, but the bottom one actually is going to kind of connect B and C because we're going to sum over D, right? So this path here actually will remain. So that will not be blocked. So that means there will exist a path between B and C. So you cannot say that B and C are independent given A. Okay, so the rule here is they're going to remove all. It's much easier actually than the belief network case. We just to assess conditional independence for Markov networks, we remove all links neighboring the variables in the conditioning set Z. So in that case, we get rid of all of the links coming out of A and D because they're the variables in the conditioning set. So we remove them, and then we just say if there's no path from any member of X to any member of Y, then this basically is conditionally independent. Otherwise, they are dependent. I'll come back to this qualification later. But in this case, there is a path BD. We could only remove these two links here, but there remains a path. So this is a bit simpler than previously. Now, there's a way to. This is the sort of more formal way to think about independence, and this is nice because this rule holds for both Markov and belief networks. Okay, so if you need just to remember one rule, this is maybe a good one to remember. Okay, so let's go back to the belief network case. So we can now ask a question. Here's a belief network on the right. Are A and I independent given F and I? So the first thing to recognize is that to answer this question, G is not going to play any role at all. Because we're interested in the marginal, because we're going to have to sum over all of the non-colored variables are going to have to be summed over. So it's clear that when you sum over G, he's just going to disappear to 1. That's obvious. So it's clear that for any variables here which are non-ancestors of these variables in the conditioning set and in A, that they're not going to play any role at all. They just will disappear immediately. So the first step is that you form what's called the ancestral graph here. You remove any node which is not in this set, x, y, and z. So is x, y, x is a set, y is a set, z is a set. Right? Just get rid of them. Right? So in this case, we can get rid of G. It has never going to play any role in the filter analysis. And then the moralization step is to add a line between any two nodes which have a common child. And remove the arrowhead. So we look for children. So this is the collider. So we need to do this. Just go back here. So we've got, if they have a common child, there's another 2 here.
And then
This one. And then we do that, and then and after doing that, we remove the arrow directions. Okay. So now we've got, if you like, the moral graph. And then we separate it. We remove all the links from Z, so the conditioning variables. So we're going to get rid of all of these, any links which are connected to the yellow nodes. Okay, and then basically, if there exists still a path from the x to y, then they are dependent. Okay, in this case, they are dependent because there is a connected path between A and I in this case. So A is dependent, and it's the other way around. This is independence, this is dependence. Okay, so it kind of makes sense, a little bit like what we were before. So, the ancestral graph, that makes a lot of sense, right? Because obviously not going to play a role. Its moralization is kind of a little bit to do with this collider effect that we were talking about before. Then the separation is nice. This is a little bit to do with path cutting effect, and then we just check. So this is a nice. I quite like this. Personally, I find it, it's quite easy to program. So if you look at my code, you will see that there's a function which checks, and given a graph, whether or not there's independence or dependence or conditional independence. It's using this algorithm. Actually, I don't use the other Perl algorithm, but it's up to you guys. I mean, I personally prefer this one. But, you may find, for the belief network case, that you like the previous path connection deseparation idea. Nice. I don't normally force you to remember, one or the other. I mean, it's up to you. So it's, I don't mind if, for example, in an exam situation, if you use one or the other technique to assess whether or not these variables are independent. It's up to you. Of course, you have to explain how you do it. That's all. If you say yes or no, that's not. Okay. So I think that's kind of nice. Okay, so good. So let's just go back to some historical stuff now. So what the heck are these? Where did these things come from? These Markov networks. Originally, they came from physics, and they were then appropriated by the machine learning community as well, back in the 1970s originally. There was a little bit of work on them in the 1980s, and I explained a little bit about this now. So I'd like to tell you about the Boltzmann machine. So this was the big baby of the 1980s. Okay, so this is like everybody wanted to work on the Boltzmann machine, it was kind of considered a very powerful thing, and it is. It's extremely powerful in terms of as a distribution as an idea. It turns out to be extremely difficult to work with. That's the problem. If we could work with this thing, we'd be very, very happy. If somehow we could figure out how to computationally work with this, we'd probably drop most of the things. It's the most interesting thing we'd like to work with, but it's problematic. So what is it? It's a distribution over, in this case, say binary variables. It can be extended to discrete variables, but let's take a binary, say 0, 1. It doesn't really matter what the two states are. And we get some parameters, W and B. So I'm writing on the right now. I'm not going to put a distribution over W and B, but I'm just going to putting them there to say that we have to know what the parameters are. And then it's going to be the form, an exponential, over some quadratic form in variables. Okay, so this Wij is just connecting variables I and j. So there's some quadratic term and some linear term. This W and its B's are given to you, they're fixed. Right? So this specifies a distribution over X, and this Z is the normalization constant. And this is sometimes also called the partition function in more physics literature. Okay, and I'm just writing I less than j here. It doesn't really matter if you write I and j. It plays no big role. You just get it's whether you count, you want to put a half or a lot in front of this sum. It's up to you. There are different conventions. The point is you just have a quadratic form here, X. That's all. And these are called weights and biases, the W and the B. And so the basic, the picture is that when people started to think about, well, when physicists started to think about brains, they thought brains look like this. I mean, from a sort of very high level perspective, you have a neuron I, and you have another neuron J. These neurons are all they're talking to each other. Maybe not all of them are talking to each other, but maybe there's some sort of structure by which the neurons are talking to each other. They're connected. And it apparently is, well, our current understanding of the brain is indeed that communication between neurons is essentially binary. So it's not that a neuron itself is a binary object, but the communication between the neurons is binary. You either send a signal of some sort of fixed amplitude in some sense, or you don't send it. It's either there or it's a binary communication mechanism. So they might have thought, well, maybe you can think about these mechanisms or this communication as essentially some kind of equivalent to having binary states. They're either firing, they're either communicating, or they're not communicating with neurons. Okay? And they're connected in some way. And so their initial model was that this form, that this is their original neural